In this video, we're going to learn about composite functions, one-to-one functions, and inverse functions. We will start with composite functions. First, we'll learn about the notation that we use to represent composite functions. This notation represents a composite function, and we read it as f of g of x. And be very careful, this open circle does not mean multiply. That's what this little warning sign says here. This open circle does not indicate that you're supposed to multiply. Instead, this open circle indicates that we're dealing with a composite function. Now we can represent composite functions using this notation, or we can use this notation. This is also read f of g of x. This notation and this notation both represent the same exact composite function. They're just two different ways to represent the same information. Now that we know the notation that's used for composite functions, let's actually use this notation to find composite functions. To start, we're given two functions here, f of x and g of x. For part A, we're not finding composite functions, we're just finding f of 4, but this will be important review when we move on to composite functions. Since I see that we're dealing with function f here, I started by copying down the function f right here. Now we're asked to find f of 4. This notation simply means that we're supposed to look at our function f, and wherever we see x, we're supposed to replace it with 4. In other words, we're plugging 4 in for x. So if we replace this x with 4, that will give us 4 squared minus 4. And then we can go ahead and compute this. 4 squared gives us 16 minus 4, and 16 minus 4 gives us 12. So we found that f of 4 is equal to 12. Now we're going to learn about the new concept, which is composite functions. Remember, this notation here, when you see this open circle here, means that we're dealing with a composite function. Now, many people like to rewrite this notation using this notation. A lot of people, including myself, find this notation a little bit easier to work with. Notice when you compare these two notations, the letters go in exactly the same order. So to rewrite this using this notation here, we'll start with the f. Then we put a set of parentheses, and inside the parentheses we put g of x. Here, instead of having an x, we have a 3, so inside the parentheses I'm going to put g of 3. Now we would read this as f of g of 3. First, we're going to work with this red expression here inside parentheses, g of 3. This is very similar to what we did over here. G of 3 means that we're supposed to go look at our function g. G of x is equal to 5x plus 1. So I'm going to start by writing that the function g is equal to 5x plus 1. But now remember, over here when we were finding f of 4, we're supposed to replace x with 4. Similarly, when we're finding g of 3, this means that we're supposed to replace the x with 3. So I've erased the x, and we're going to replace it with 3. Now we simply compute this. 5 times 3 will give us 15 plus 1, and 15 plus 1 will give us 16. So first we worked inside parentheses to find g of 3, and we found that g of 3 is equal to 16. So now I'm going to go ahead and rewrite this problem, but I'm going to replace g of 3 with 16, and that will look like this. Again, we just found that g of 3 equals 16, so I just replaced g of 3 with 16. Now we're going to find f of 16, which is a problem just like what we did over here. Since I see an f here, that means we're supposed to look at function f. We see here that f of x is equal to x squared minus 3. So I'm going to start by writing that function f is equal to x squared minus 3. Now, this notation means that we're supposed to replace x with 16. So I've erased the x, and I've replaced it with 16. Now we just need to go ahead and compute this. 16 squared is 256, and then we'll bring down the minus 3, and 256 minus 3 gives us 253. And this is our final answer. Some people like to think of functions as machines, and here's a way we can visually picture what we just did. So again, we were asked to find the composite function f of g of 3. First, we rewrote this notation using this notation here, and first we worked inside parentheses to find this red quantity here, g of 3. This means that we're supposed to plug the number 3 into our function g. So you can imagine taking 3 and plugging it into the function g. When we did that, the output or the answer was 16. So that pumped out the number 16. So once we found g of 3, we're then going to plug that answer into function f. So we took our answer for g of 3, which was 16, and we plugged that into function f, and that gave us our final answer, 253. So this notation simply means find g of 3 and plug your answer into function f. Let's take a look at these two problems here. I'm going to recommend that if you see this notation here, you rewrite it using this notation. So all the letters go in the same order. So we'll start by writing the g, then we'll draw some parentheses, and then inside the parentheses we'll put f of negative 2. Now, first, we work inside parentheses. So we're going to focus on finding f of negative 2. So we need to use our function f. F of x is equal to x squared minus 3. So I'm going to start by copying down x squared minus 3. Now this notation here means that we're supposed to replace x with negative 2. So I've erased our x and we're going to replace it with negative 2. Whenever you're raising a negative number to an exponent, make sure to put the number in parentheses so that you're raising the whole number, including its negative, to your exponent. Then we just need to compute this. Remember, the square applies to both the negative and the 2. That means we're taking negative 2 times negative 2, which gives us a positive 4, and then we'll bring down the minus 3, and 4 minus 3 will give us 1. So we worked inside parentheses and we found that f of negative 2 is equal to 1. So now I'm just going to copy down this exact original statement here, but I'm going to replace f of negative 2 with 1. Now we're supposed to find g of 1. Well, this just means go look at your function g and replace x with 1. I'm going to start by copying down that g is equal to 5x plus 1. And now we're supposed to replace x with 1. So I've erased the x and replaced it with 1. Now we just need to compute this. 5 times 1 plus 1 gives us 6. So again, this notation here, which we just rewrote using this equivalent notation, simply means find f of negative 2, and whatever your answer is, you're going to plug it into g. So we found that f of negative 2 was 1, so then we just plugged 1 into g. Let's take a look at this problem here. First, I'm going to rewrite it using this notation here. All the letters go in the same order. So we'll start with g, then we'll draw our parentheses, and then inside the parentheses we'll put g of negative 8. Now first we'll work inside parentheses with this quantity in red. So we need to find g of negative 8. That means we're going to go look at our function g, which is 5x plus 1. And wherever we see x, we need to replace it with negative 8. So I've erased our x, and I've replaced it with negative 8. Now I'm going to go ahead and compute this. This will give us negative 40 plus 1, which equals negative 39. So we found that g of negative 8 is equal to negative 39. Now let's go ahead and replace this red quantity, g of negative 8, with negative 39. That gives us g of negative 39. This means go look at our function g, which is 5x plus 1. So I'm going to start by writing 5x plus 1, and we're supposed to replace x with negative 39. So I've erased our x, and I've replaced it with negative 39. Now we just need to compute this. And if you take 5 times negative 39 plus 1, you'll get negative 194 for your final answer. So again, this notation here, which we just rewrote using this equivalent notation, simply means find g of negative 8 and plug that into function g. So we found that g of negative 8 was negative 39, and we went ahead and plugged that into function g. Next, instead of looking at composite functions where we have a number here, like we did in these three problems. On this page, we're going to look at composite functions where we have a variable here instead of a number. Now, before we look at the composite functions, we'll first review an important concept. So here we're asked to find f of x plus 1. This is not a composite function, this is just review. The notation f of x plus 1 tells us to go look at our function f, and here's the given function f. And wherever we see x, we're going to replace it with x plus 1. So we're plugging x plus 1 in for x. That will leave us with 2, and we're going to replace x with x plus 1, and then we'll bring down our plus 7. So with this notation, whatever you see inside parentheses, whether it's a number or a variable expression, you're going to take what's inside the parentheses and plug it in for x. Then from here, we just need to simplify. If we distribute the 2 here, that will give us 2x plus 2, and then we'll bring down the plus 7, and this will simplify to 2x plus 9. Now we'll use what we reviewed here as we look at these composite functions. We're going to start this composite function the same way we started the composite functions on the previous page. We're first going to rewrite it using the other equivalent notation. We start with the f, then we draw our parentheses, and inside the parentheses we put g of x. We're going to start with what's in red inside the parentheses. What is g of x? Well, as it says up here, g of x is equal to x squared minus 4x plus 5. So I'm just going to write that here. G of x is equal to x squared minus 4x plus 5. So we know from the given information that g of x is equal to this expression here. So now I'm going to rewrite this original expression, but I'm going to replace g of x with x squared minus 4x plus 5. Again, I've just copied down this original expression, but I've replaced g of x with this expression here. So I've rewritten g of x with this expression. Now, this problem here is just like the review problem we saw over here. This review problem said, look at function f, and wherever you see x, replace it with x plus 1. This says the same thing. This says, look at your function f, and wherever you see x, we're going to replace it with this expression here. So I'm going to start by just copying down what f of x is equal to. F of x is equal to 2x plus 7. Now I'm going to erase the x and replace the x with x squared minus 4x plus 5. Now we just need to simplify and we're finished. To simplify, let's distribute the 2. That will give us 2x squared minus 8x plus 10, and then we'll bring down the plus 7. And then we can combine the 10 plus 7 to give us 2x squared minus 8x plus 17. So if we look at the big picture here, f of x plus 1 means go look at your function f, and wherever you see x, replace it with x plus 1. This notation means the same thing. F of g of x means go look at your function f, and wherever we see x, we're replacing it with g of x. Well, what is g of x? G of x is this expression here. So this means go look at your function f, and wherever you see x, we replaced it with this expression right here. Let's take a look at this problem here. First, I'm going to rewrite this notation using the other equivalent notation. All of the letters will stay in the same order. So we'll start with g, then we'll write our parentheses, and inside the parentheses, we'll put f of x. Now what this means, the big picture, is that we're supposed to go look at our function g, and wherever we see x in our function g, we're supposed to replace it with f of x. Let's take this piece by piece. First, we always work with what's inside parentheses in red. So let's ask ourselves, what is f of x? Well, that information is just given in the problem. F of x equals 2x plus 7. So I'm going to write that right here. So we can go ahead and replace f of x with 2x plus 7 because they're equal. So I've rewritten this exact expression, but I've just replaced f of x with 2x plus 7, since f of x is equal to 2x plus 7. Now, this problem here is very similar to this review problem that we looked at up here. This just means go look at your function g. So I'm going to start by copying down our function g. G is equal to x squared minus 4x plus 5. Then, wherever we see x, I'm going to erase that x and replace it with 2x plus 7. That gives us this expression here. Now we just need to simplify. Now the most common mistake here is that students will try to distribute this exponent. But remember, exponents don't distribute. Instead, 2x plus 7 squared means that we're supposed to take 2x plus 7 times itself. So I'm going to rewrite it as 2x plus 7 times 2x plus 7. Then let's go ahead and distribute this negative 4. Negative 4 times 2x will give us negative 8x, and negative 4 times 7 will give us negative 28. And then I'll bring down the plus 5. Now I'm going to speed up the video as I FOIL this out and combine like terms to simplify. After we FOILed this expression and then combined all of the like terms, we get our final answer here. Let's take a look at this example here. First, we'll rewrite it using the other equivalent notation. We'll start with f, then draw our parentheses, and inside the parentheses we put f of x. Now, what does this mean in general? Remember, whatever is in red inside parentheses, that's what you're going to be plugging in. This tells us to plug f of x back in to function f. Let's take that step by step. We always start with what's inside parentheses in red. What is f of x? Well, we're told in the problem that f of x equals 2x plus 7. So now that we know that f of x equals 2x plus 7, we can go ahead and replace f of x with 2x plus 7. And so instead of writing this original expression here, I've just replaced the red f of x with 2x plus 7. This means go look at your function f. Function f is equal to 2x plus 7. Now this notation means we're supposed to replace x with 2x plus 7. So I'm going to go ahead and erase the x and replace it with 2x plus 7. Now from here, we just need to simplify. So I'm going to speed up the video as I distribute and then combine like terms. And after we simplify, we get the final answer, 4x plus 21. So again, this notation just means take your function f of x, which is 2x plus 7, and plug it into function f. So in our function f, wherever we saw x, we replaced it with 2x plus 7. Now this next page is review of the 2 previous pages. I recommend that you pause the video and try problems A, B, C on your own, and then play the video when you're ready to check your answer. So we'll go through these problems quickly since these are review of the past 2 pages. I'll start by rewriting this problem using the other equivalent notation. Then we always start with what's in red inside parentheses. As the original problem states, f of x is equal to 2x plus 3. So let's go ahead and replace f of x with 2x plus 3. So instead of writing g of f of x, I've written g of 2x plus 3. Now this notation here means go look at your function g. We see that function g equals x squared. So I'm going to start by writing that. Then we're supposed to replace x with 2x plus 3. So I'm going to erase the x and replace it with 2x plus 3. Now again, be careful here. Exponents don't distribute, so please don't try to distribute this exponent. Instead, 2x plus 3 squared means that we're supposed to take 2x plus 3 times itself. And now I'll speed up the video as I FOIL and combine like terms. and this is our final answer. Next, let's take a look at this problem here. First, we'll rewrite it using the other equivalent notation. This means we're going to be plugging the function g of x back into the function g. So we always start with the expression in red inside parentheses. We're told in the original problem that g of x is equal to x squared. Let's go ahead and replace g of x with x squared. So instead of writing g of x, we've written g of x squared. Now this notation means go look at your function g. Function g is equal to x squared. Then wherever we see x, we're supposed to replace it with x squared. So I'm going to go ahead and erase the x and replace it with x squared. And from here, we just need to simplify. Remember, the rules of exponents say that when you raise an exponent to an exponent, to simplify, you just multiply those two exponents together. So 2 times 2 gives us 4, leaving us with x to the 4th. And if we look at this last problem together, now notice this problem differs from the previous 2 problems, because in the previous 2 problems we had an x here, versus in this problem we have a 12. We start the same way. We'll rewrite this expression using the other equivalent notation. Now first, we work with what's inside parentheses in red. What is g of 12? Well, g of 12 means go look at our function g, and wherever we see x, we're replacing it with 12. So that means instead of having x squared, we'll have 12 squared. And 12 squared simplifies to 144. So we know that g of 12 is equal to 144. So let's go ahead and rewrite this expression, but we'll replace g of 12 with 144. Now we need to find f of 144. This simply means go look at our function f. Well, our function f equals 2x plus 3. And wherever we see x, we're supposed to replace it with 144. So I'm going to erase the x and replace it with 144. And now I'll speed up the video as I simplify this expression. And our final answer is 291. Let's take a look at the next page. Now in chapter 2, we learned about functions. On this page, we will quickly review functions, and then we will discuss a special type of function called a one-to-one function. Remember, a function is a relation in which each element of the domain, or in other words, each x value, corresponds to exactly one element of the range, or in other words, y value. Let's look at these maps down below and determine which of them represent functions. All you need to ask yourself is, does each x correspond to exactly one y? If the answer is yes, then we have a function. Let's see. This x corresponds to exactly one y. This x corresponds to exactly one y, and this x corresponds to exactly one y. Therefore, this is a function. Let's take a look at this map. This map is a function if each x corresponds to exactly one y. This x corresponds to exactly one y. x1 corresponds to y1. This x corresponds to exactly one y. x2 corresponds to y1. And this x corresponds to exactly one y. x3 corresponds to y3. It doesn't matter that these two x's correspond to the same y. Doesn't matter. The only requirement for functions is that each x corresponds to one y. So this is a function. If we look at this map here, to determine if it is a function, we ask, does each x correspond to exactly one y? Let's see. x1 corresponds to 2 different y's. x1 corresponds to both y1 and y2. So this is not a function because there's an x value, specifically x1, that corresponds to more than one y. Now we've reviewed functions, now we're going to look at a special type of function called a one-to-one function. Only certain functions can be classified more specifically as a one-to-one function. A relation is a one-to-one function if the relation satisfies the above definition. The above definition is the definition of a function. This makes sense. If it's a type of function, then it must satisfy the definition of a function. But that's not all. To be a one-to-one function, not only does it have to satisfy the definition of a function, but also each element of the range, in other words, each y value, must correspond to exactly one element of the domain, in other words, x value. To put that simply, to be a one-to-one function, it must be a function in the first place, which means that each x must correspond to exactly one y. If that's the case, it's a function, but to be more specifically a one-to-one function, the reverse also has to be true. Each y value must correspond to exactly one x value. So if each x corresponds to exactly one y, and the reverse is also true, each y corresponds to exactly one x, then you have a special type of function called a one-to-one function. Let's look at these maps and determine if they represent one-to-one functions. First, it has to be a function in the first place, so each x must correspond to exactly one y. We already determined that it satisfies the requirement for a function, but to be one-to-one, the reverse must also be true. Each y must correspond to exactly one x. Let's see, this y corresponds to exactly one x. This y corresponds to exactly one x, and this y corresponds to exactly one x. So yes, this is a one-to-one function. And the reasoning is because the above is true, each x corresponds to exactly one y, and the reverse is also true, each y value corresponds to exactly one x value. Next, let's determine if this map represents a one-to-one function. To be a one-to-one function, it must be a function in the first place. We already determined it is a function. So we know that each x corresponds to exactly one y, but to be one-to-one, the reverse also has to be true. Does each y correspond to exactly one x? Let's see. y1 corresponds to two different x values. y1 corresponds to x1 and also x2. So right away, I can say that this is not a one-to-one function. While it is a function, it's not one-to-one, since y1 corresponds to more than one x value. Lastly, let's determine if this map is a one-to-one function. Well, in order to be a one-to-one function, it has to be a function in the first place. This is not a function, so since this is not a function, it's definitely not a one-to-one function. Next, we're going to learn about inverse functions. And when we talk about inverse functions, we'll learn why one-to-one functions are important. Let's start with the notation that we use to represent an inverse function. This notation here represents an inverse function. Now be very careful. I've put this warning sign here because a lot of people mistakenly think that this notation means f to the negative 1. And they'll think that you're supposed to raise your function f to the negative 1 exponent. That is incorrect. Unfortunately, the notation for inverse functions can be a bit misleading. It looks like this negative 1 is an exponent, but this negative 1 does not represent an exponent. This notation here means inverse function. Now we'll start with the definition of an inverse function, and then we'll look at examples. The definition states, if f is a one-to-one function with ordered pairs of the form a, b, then the inverse function, denoted using this notation, is the set of ordered pairs of the form b, a. Now this definition makes it sound more complicated than it is. When you're finding the inverse function, you're just switching the x and y coordinates. Now, an important note here, only one-to-one functions have inverse functions. Now, I'm just going to tell you that right now but on the next page, I will explain why that's the case. So, to find the inverse of a one-to-one function, you just switch the x and y values. In other words, to find the inverse of a one-to-one function, interchange the elements of the domain with the elements of the range. So, let's find the inverse of this one-to-one function. We're told the function is a one-to-one function, and that's helpful because in order for this to have an inverse, it must be a one-to-one function. So we're given that this is a one-to-one function, so we can proceed to find the inverse function. First, I'm just highlighting all of the x values, and then I've highlighted all of the y values. Now it's really easy to find the inverse function. All you have to do is switch the x and y values within each ordered pair. So I'll start by drawing this curly bracket. Remember, we use this curly bracket whenever we're dealing with sets. And here we're dealing with a set of ordered pair, so we'll use this set notation, this curly bracket. First, I'll examine this ordered pair, and I'm going to switch the x and y coordinates. So the y coordinate 9 becomes our x coordinate, and the x coordinate -2 becomes the y coordinate in our inverse function. Then I'm going to look at this ordered pair and switch the x and y coordinates. That gives us 2, -1. Next, let's switch the x and y coordinates of this ordered pair to get 11, 0. And lastly, let's switch the x and y coordinates of our last ordered pair to get -5, 1. And then we'll put the curly bracket to close our set notation. So, to find the inverse function, we just need to switch the x and y coordinates. Now, we've found the inverse function from a set of ordered pairs. Next, we're going to practice finding the inverse function from a graph. Notice here we're told that this is a one-to-one function, so we know automatically that it will have an inverse function. When you're asked to find an inverse function, you'll typically be told that the given function is one-to-one, so you'll know right away that it does have an inverse function. So I'm going to start by listing the ordered pairs of the given function: -3, -2, -1, 0, and 4, 2. Now this graph has infinitely many more ordered pairs on it, but these 3 given ordered pairs should be enough information to allow us to sketch our inverse function. So to find the inverse function, we just need to switch the x and y coordinates in each ordered pair. So if we switch these x and y coordinates, we would get -2, -3. If we switch these x and y coordinates, we would get 0, -1. And if we switch these x and y coordinates, we get 2, 4. Now let's plot these points. First, we'll plot -2, -3 by going -2 along the x-axis, and then we'll go down 3 along the y-axis. Then I'm going to plot the ordered pair 0, -1, and lastly, I'm going to plot the ordered pair 2, 4. Now the inverse function will have the same shape as our original function. So notice these 3 ordered pairs were all connected with straight lines. So for the inverse function, we'll do the same. We connect our 3 ordered pairs with straight lines. And so this function in red is our inverse function. So far, I've just told you that only one-to-one functions have inverse functions. If you have something that's not a one-to-one function, it will not have an inverse function. On the next page, I'm going to explain why that's the case. So the question we're asking here is, why must a function be one-to-one in order to have an inverse function? To answer that question, we're going to see what happens if we try to find the inverse of a function that is not one-to-one. So here's the function that we start out with. If function f is a one-to-one function, then it will have an inverse function. If function f is not a one-to-one function, then it will not have an inverse function. Let's first ask, is function f a one-to-one function? Well, we've practiced how to use a map to determine if a function is one-to-one. In the rectangle on the left, we list the x values, and in the rectangle on the right, we list the y values. So first, I'm just going to copy down each x value into this shape here. We'll start with -2, then -1, then 0, then 1, and then 2. The trick when you're drawing maps is that we never repeat any x values in your map. Notice there were no repeated x values, so we didn't have to worry about that. But let's say the x value 1 appeared in more than one ordered pair, you would only list the x value 1 once in your map. In this rectangle on the right, we're going to list the y values. Same goes for y values. You only list each y value once. If you see any repeated y values in your ordered pairs, you still only list the repeated y values once. We'll start with the y value 4, then the y value 1, then the y value 0, then we have the y value 1, which is a repeated y value. We already listed that y value, so we do not list it again in our map. Then we see the y value 4, which is another repeated y value. We already listed the y value 4, so we don't repeat it in our map. Now, connect each x value to its corresponding y value. The x value -2 needs to be connected to the y value 4. The x value -1 needs to be connected to the y value 1. The x value 0 must be connected to the y value 0. The x value 1 must be connected to the y value 1. And the x value 2 must be connected to the y value 4. Now we drew a map because we're simply trying to figure out if this original function is one-to-one. Remember, to be a one-to-one function, it has to be a function in the first place, which means each x must correspond to exactly one y. Let's see if that's the case. The x value -2 corresponds to one y value 4. The x value -1 corresponds to one y value 1. The x value 0 corresponds to one y value 0. The x value 1 corresponds to one y value 1. And the x value 2 corresponds to one and only one y value 4. So this is a function, but is it more specifically a one-to-one function? In order to be a one-to-one function, it has to be a function in the first place, so each x value must correspond to exactly one y value. We said that that is true, but to be a one-to-one function, the reverse must also be true. Y must correspond to exactly one x. Let's see if that's true. Right away, I see a problem. The y value 4 corresponds to more than one x. The y value 4 corresponds to the x value -2 and also to the x value +2. And there's another problem here. The y value 1 corresponds to the x value -1 and the x value 1. So this is not one-to-one. So let's review what we've done so far. On the previous page, I told you that if a function is not one-to-one, it will not have an inverse function. On this page, we were given a function, and from the map, we determined that our given function is not one-to-one. So that means that this function will not have an inverse function. But my question is, why not? Let's try to find an inverse function of this function here that's not one-to-one. So we're going to try to find the inverse function. You just need to switch the x and y coordinates in each ordered pair. So for this ordered pair, if we switch the x and y coordinates, that would give us the ordered pair 4, -2. If we switch these x and y coordinates, that would give us the ordered pair 1, -1. If we switch these x and y coordinates, we'd get 0, 0. Switch these, we'd get 1, 1. And switch these x and y coordinates, we'd get 4, 2. Now I'm confused because we said that this function is not one-to-one, so it should not have an inverse function. But it seems like we just easily found the inverse function. Well, let's try to look at the graph of this to see why it's not an inverse function. I'm going to plot each of these ordered pairs. Now remember, the inverse function will have the same shape as the original function, it just will be oriented differently. So we know we'll have a U-shaped graph, but it'll just be oriented differently. So I'm going to connect these points with a sideways U here. Now I'm still confused. We said that if a function is not one-to-one, and this original function in yellow here was not one-to-one, then it should not have an inverse function. But it seems like we successfully switched the x and y values, and we even graphed it. So why can't we call this red graph an inverse function? Well, to be an inverse function, it has to be a function. Inverses are defined as being functions. Remember, if you want to know if your graph is a function, you can use the vertical line test. The vertical line test says that if any vertical line passes through more than one point on your graph, then your graph is not a function. Here's an example of a vertical line that passes through our graph, and it touches the graph in more than one point. This graph in red does not pass the vertical line test, so it's not a function. If it's not a function, then there's no way we can call it an inverse function. So a function must be one-to-one in order to have an inverse function. Because if your function is not one-to-one, like this yellow function here, when you try to find the inverse function, you'll get something that doesn't pass the vertical line test, so it will not be a function, like we saw here, and you can't call something an inverse function if it's not a function. So this shows why a function must be one-to-one in order to have an inverse function. Now, so far, we've learned how to find the inverse function given a set of ordered pairs, given a graph. The last step is to find the inverse function given a function's equation. I've typed out the steps that we're going to follow in order to find the inverse function given an equation. Notice for the problems that you'll see, you'll typically be told that your given function is one-to-one. So you won't have to do any extra work to determine if your function is one-to-one. You'll be told that in the problem. So since it's given that the function is one-to-one, you can right away proceed and find the inverse function. First step when you're trying to find the inverse function, as it says here, we're going to replace f of x with y. This is simply going to make the problem easier to work with. Remember, f of x just means y, so they're replaceable with one another. So I've started by copying down the original given function, and I'm going to go ahead and replace f of x with y to give us y equals 3x minus 4. Step 2 is the key. We know that in order to find the inverse function, you just switch the x and y values. So for step 2, we're going to interchange, or in other words, switch x and y. So where I see y, I'm going to write x, and where I see x, I'm going to write y. So that will give us 3y minus 4. Now that we've switched the x and y's, we can move on to step 3. Now in step 2, we've found the inverse function, because to find the inverse function, you just have to switch the x and y's. Step 3 is just so that we can write our final answer in proper form. So to write our final answer in proper form, we need to solve for y, because when we're writing inverse functions, we like them to be solved for y, not for x. So first I'm just going to copy down our given function here. Then we want to isolate or solve for y. I'm going to start by adding 4. That will leave us with x plus 4 equals 3y. Now we've almost isolated y, but we just need to divide by 3. And that leaves us with x plus 4 over 3 is equal to y. When we write our final answer using function notation, we typically like the y to be on the left side. So I'm just going to swing this around the equal sign and write it as y equals x plus 4 over 3. Again, we found the inverse in step 2 by just switching the x and y's. Step 3 is just so that we can write our final answer in the proper form. We like our final answer to be solved for y. Now we're almost done, but we'll be expected to write our final answer using function notation. So for step 4, we're going to replace y with this notation, which is read f inverse of x. So I'm going to copy down this expression that we left off with right here. And now we'll replace the y with f inverse of x. This notation is more specific because it tells the reader that this is the inverse function. Now, it's important to know that for these problems, the answer can often be written in different formats. So this is correct, but it's useful to know that you might check your answer for this problem in the textbook, and the textbook's answer might look different from yours. You could split this apart and write it as x over 3 plus 4 over 3, and that would be an equivalent correct answer. You can see that since these two fractions have the same denominator, you could just combine them by keeping the denominator and adding the numerators, and you would get this exact expression here. So these are equivalent and both will be accepted. Let's try one last problem together. Here, we're finding the inverse function, and again, we're told that this is a one-to-one function, so we know automatically that it will have an inverse function. I encourage you to pause the video, try to solve this problem on your own, and then play the video to check your answer. To find the inverse function, we're going to follow the same 4 steps that we used on the previous page. Here for step 1, we're using h of x instead of f of x. We're going to start by replacing h of x with y. This is just going to make our problem easier to work with. So I'm going to start by copying down the original given function right here, and we're going to replace h of x with y, which gives us y equals 2 over x plus 3. For step 2, we get at the heart of inverse functions. To find the inverse function, you just need to switch the x and y. So where we see y, we're going to write x, and where we see x, we'll write y. So that will give us 2 over y plus 3. Now we've found the inverse function. It's just that this inverse function is not written in the format that we want it in. So for step 3 and 4, we're just going to be rewriting this in the correct format. For step 3, we're going to solve for y. In other words, we want to isolate y. I'm going to start by copying down this equation that we left off with right here. Now, when we solve for, or in other words, isolate y, we do not want y to be in the denominator. So we need to get y out of the denominator. To do that, let's multiply this side by y plus 3. And what you do to one side of an equation, you also have to do to the other side of the equation. So we have to multiply the left side of the equation by y plus 3. Let's see what that gives us. To start, I'm just going to leave this left side of the equation as is, as x times y plus 3. On the right side, the y plus 3 in the denominator cancels with this y plus 3 in the numerator, leaving us with 2. Now we're moving in the right direction here. We know that in order to solve for, or in other words, isolate y, we can't have y in the denominator. So by multiplying both sides by the denominator here, we now no longer have y in the denominator. Next, we need to actually solve for, or in other words, isolate y. There's 2 different approaches we could take here. I'll show you both. Method 1 is a little bit quicker. I'm going to start by copying this equation down here. Now the goal here is to isolate y. So to isolate y, I'm going to start by dividing by x. These x's will cancel, leaving us with y plus 3 is equal to 2 over x. Now we're really close here. To isolate y, we just need to subtract 3. And that will leave us with y is equal to 2 over x minus 3. So this was one approach we could use to isolate y from this equation here. Let me show you another approach, and you can pick which method you prefer. I'll start by copying down this given equation right here. Now our goal here is to isolate y. Some of you might be tempted to start by distributing the x. So let's try that. If we distribute the x, x times y will give us xy, and x times 3 will give us a positive 3x, and then we'll bring down the 2. Now, remember our goal here is to isolate y. So let's start by getting rid of this 3x here. So I'm going to subtract 3x from the left and subtract 3x from the right. That will leave us with xy. These 3x's will cancel. We'll bring down the equal sign, and here we'll have 2 minus 3x. Or if you want to write it as negative 3x plus 2, you can do that instead. Now we're getting close. The last step to isolate y, since y is being multiplied by x, to get rid of that x, let's divide by x. Now we also have to divide the right side by x, and you can do that in 2 different ways. You can either divide each term individually by x, and if you do that, you'll get this exact same expression we did over here. Alternatively, instead of dividing each individual term by x, we can just divide this whole expression by x, and then let's see, these x's will cancel, leaving us with y equals, and this expression we can just leave as is, 2 minus 3x over x. Now notice, using method 1 and method 2, our answers look a little bit different, but they are equivalent. If we got a common denominator and combined these, we would end up with this expression here. Now we're almost done, but remember our final answer should be written using function notation. So for step 4, we're going to replace y with h inverse of x. So I'm going to start by copying down our two answers here. These are equivalent. You don't need to give both answers. They're just two different ways to write the same answer. So depending on which approach you used in step 3, your answer might have looked like this, or your answer might have looked like this. Then we'll replace the y with h inverse of x. So again, you only have to give one of these answers. You don't have to give both. Either this answer for your final answer would be correct, or this answer for your final answer would be correct. And there are even some other alternative equivalent ways that you could also write your final answer.